Hi, everyone. It is with great pleasure that I introduce you to Professor Andrew Jordan. Professor Jordan has dedicated his academic career to foundational problems in quantum physics, providing a refreshing perspective to these problems by formulating new questions, solving previous debates, all of this using the tools that follow from quantum optics, condensed matter physics, and overall theoretical quantum physics. What is more refreshing is that always he goes to great lengths to ground his findings on both practical and experimental realizations. Now, this broad perspective is perhaps better explained from his academic career path. Professor Jordan obtained his bachelor's degree from Texas A&M University in 1997, before moving to the University of California, Santa Barbara, to obtain his PhD under the supervision of Mark Zretnicki from the field theory books that you have all used. He then moved to the University of Geneva to work as a postdoctoral researcher in the group of Marcus Bodecker, where he started a fruitful collaboration that has led to important contributions, including the connection between entanglement and energetics, stochastic path integral formulations of counting statistics, and more recently, the study of nanoscale heat engines. After his work in Geneva, Professor Jordan took a position at the University of Rochester, where he further developed his ideas and contributed to themes of nanophysics, which addresses fundamental physical problems that occur when a macroscopic object is miniaturized, weak measurements, which make predictions about the random natures of continuous measurements over some time period, and overall random processes in nature. He became a full professor in 2015 and then joined Chapman University in 2021 as co-director of the Institute for Quantum Studies and as a professor of physics. Professor Jordan has received an NSF Career Award, the University of Rochester Department of Physics and Astronomy Teaching Excellence Award, and was named as Simon Fellows in Theoretical Physics. He was given the Kennedy Chair in Physics at Chapman in 2024 and is a member of the Physical Society and Optical Society. He became a managing editor for Quantum Studies, Mathematics, and Foundations, and he's a co-editor-in-chief and was appointed as the divisional associate editor in Foundations of Quantum Mechanics for Physical Review Letters. Today, Professor Jordan is going to tell us about his book, Quantum Measurement, Theory and Practice, which was published just last year with Cambridge University Press. He wrote this book together with Professor Irfan Siddiqui, and as you are about to see, this book presents a fascinating exploration of quantum measurements. Perhaps the importance of this book is better summarized from an excerpt of the book itself, which goes as follows. Progress in quantum mechanics, as science in general, can only be made by pushing the limits of a theory, both practical and conceptual, but asking questions that have never been asked, proposing new kinds of experiments, and searching for new phenomena in the laboratory. We can hope to come to a better understanding of the physical world itself. With these words, I would like to leave you with Professor Jordan.
Okay, thank you, Ricardo, for this very thoughtful and detailed introduction to my career and the talk I'll give to you today. It's a great pleasure to be here in Mexico City. I've been to Mexico a few times. I gave some lectures sponsored by the CONACYT in Cancun a few years ago, but this is my first visit scientifically to Mexico City. But I realize it's so easy to get here. I live in Southern California, so I hope it will not be my last visit. So the topic, as Ricardo already very eloquently spoke about, is my new book, Quantum Measurement, Theory and Practice. I want to give you a taste of some of the physics that we've been able to understand and explore the past few decades. So let's see here. So first of all, thanks for this beautiful advertisement you made for my talk. I was really impressed. This really nice appearance on your university website. So thank you for putting that together. I'm happy to be here. Where is Chapman? So I'm at Chapman University. For the many years I was at the University of Rochester in New York, which is well known for its history in quantum optics. I moved to Chapman a few years ago to start continuing my career in quantum physics. It's here near Los Angeles, just south of the Los Angeles area, in a city called Orange. Here's San Diego, here's Los Angeles. I live in Laguna Beach where all the little hearts are. And it's a beautiful little private university. I have a nice institute there that I direct. So whenever you're coming up to the United States, please let me know. I'll be happy to host you there. As Ricardo already mentioned, I work in many areas of physics. I'll just give you a brief introduction to some of the things I work on. So the topic of the talk today is quantum measurement and control, a topic of areas we call quantum trajectory theory, and this formalism that I developed in my group, the stochastic path integral formalism Ricardo mentioned. I also work in quantum metrology, so how to use quantum physics to make very precise measurements, to increase the precision and make new kinds of sensors, and also in work together with experimentalists to try to make really top-of-the-line experiments in this area. And then more recently, we did some work on optical super resolution and what we call super radar to try to get super resolution in radar ranging experiments as well. I also work in quantum thermodynamics, so this is work that I started back when I was a postdoc with Marcus Bodeker, and I continue to this day, thermoelectricity, mesoscopic heat engines, quantum thermal transport, and mesoscopic structures. And then finally, what my institute is really devoted to, topics and foundations of quantum mechanics, foundational questions like, what does the quantum state mean? Is it something that exists out there independently of us, or is it our construction? What is the nature of quantum mechanics? And then other topics that are mentioned here. So that gives you a brief outline in some of my research interests over the years. And then for today, the goal is talking about my new book and introducing you to some of the basic concepts and some of the topics there. Because this is a colloquium level talk, I'm not going to give very mathematical, I'm trying to give you the conceptual foundations of this. So I'll walk you through some of the basic ideas behind this area, and then as a kind of fun conclusion to the talk, I'll make some connection about the book cover, a connection between art and science. And Ricardo has very kindly brought his copy of the book here. So this is my book, so I'll pass it around, and you can, as long as you don't steal it, you have to give it back to Ricardo at the end of the talk. You can take a look at it. Okay. Good. Good. So this is this is the outline for the talk today. So I think I already talked about that. So here is the book. This is my co-author. This is Irfan Siddiqui. He's my neighbor to the north at University of California, Berkeley, in the San Francisco Bay Area. And the book was published by Cambridge University Press this past year. So here is the timeline of the book. Ricardo was asking me, Andrew, what was your experience writing the book? And this is just to give you a warning that it takes a lot longer than you think it will. It began with a French scientist, Daniel Estève, writing in 2019, telling both Irfan and me independently, Andrew, you've done all this great work. People need to know more about it. You should write a book. And this is all the rest of the stuff that we went through, working with Cambridge University Press, writing initial drafts, getting figure permissions, things you don't think about, writing an index, all this good stuff that goes into the book, but you don't ever really think about. So it took a long time. And here's Irfan and I celebrating. This is in Laguna Beach, where I live, at a resort hotel there, celebrating. We just finished writing some of the book together, finished writing our last chapter. Okay, so here is the outline of the book. It's divided into fundamental principles, advanced topics, and applications and implementations. It's meant to be used as a textbook, so if you want to teach students with it, it has exercises that you can use and work out for yourself. And I'll be working through some of the material in the chapters, and just some motivating questions I'll write there on the left. And I like to ask these questions because the only way we learn is if we learn through question and answer. We learn through the Socratic method. So if someone asks you a question and you don't know the answer to that, it prompts you, it stirs your curiosity, you want to learn more about the world. And so here's some questions, and if you're intrigued by these questions, this is a way of learning more about the answers to the questions. So let's begin. Basically the summary and the subject matter is we give a physics first approach. So very often in these books on quantum physics or quantum measurements, either the books are very mathematical or they're very philosophical, and we wanted to do something very different, which was to talk about the physics first. So what phenomena do we observe in the laboratory? Why are the phenomena interesting? What strikes us as puzzling about those effects? And then how do we begin to systematize that and make a scientific description about that? Okay? So these are some of the topics of the physics, ranging from more philosophical ideas like Schrödinger's cat, the structure of the atom, how the atomic theory is successful, and then what that points to. So it's all about this wave function psi, and it has the possibility to keep collapsing on us. It has this fainting spells. It collapses, it collapses, it collapses. What is this collapse all about? I'm going to tell you a little bit about that in the course of this colloquium. So let's begin with what I call the cardinal properties of textbook quantum measurement. So if you pick up a book on quantum measurement, here's what I distill out to be the essential cardinal properties. The first property is it's projective. So we obtain perfect knowledge of a property of the quantum system we're measuring with an associated mathematical projection of the quantum state onto an eigenstate of the observed property. It's irreversible, and here I'm paraphrasing, I'm stealing from John Wheeler, who's paraphrasing Niels Bohr. He says, we are dealing with an event that makes itself known by an irreversible act of amplification, by an indelible record, by an act of registration. So this word indelible, you can think about permanent marker. I write in permanent marker. Once I write, I cannot unwrite. And then finally, instantaneous. I say it's latent in the writings of Einstein, but made explicit by Heisenberg. Quote, the experiment. So Heisenberg is envisioning this kind of scattering experiment where I have a target, I send out a particle, it's described as a wave packet. There is the possibility of reflection of the wave packet, the possibility of transmission of the wave packet. So the wave packet exists essentially across all of space. And so he's thinking about this experiment, and he writes, the experiment at the position of the reflected packet, that is, if I detect the particle as here and not there, thus exerts a kind of action, reduction of the wave packet, that's that collapse I was talking about, at the distant point occupied by the transmitted packet, and one sees that this action is propagated with a velocity greater than that of light. So concluding that the measurement must be, in some sense, instantaneous. All right, so that's sort of the state of wisdom, essentially in textbook quantum mechanics. But what we've learned is that we've learned a lot more about how measurement happens. And in particular, I'll be telling you about it in this colloquium, so-called generalized weak or continuous measurements. And these are new kinds of measurements, and they're intriguing because they break all three of these cardinal properties. No longer is the measurement instantaneous. It must take place over a period of time. No longer is it irreversible. It turns out these measurements can be probabilistically reversed. And no longer is it projective and disturbing. It can actually be minimally disturbing, and I can actually tune by how much the measurement disturbs. Okay? And what do I mean by this generalized measurement? It's essentially any situation where there is some imperfect correlation between the state of the quantum system and the reading on the measurement device. So that's what I'll be talking about in more detail. So we can begin by thinking about the founders of the field, back with the Bohr model of the atom in the 1910s, quickly followed by the work of our heroes, Niels Bohr, Albert Einstein, Erwin Schrödinger, Max Born, many of these great pioneers in the field, the founders. I say it begins with the complementary principle of Bohr, the uncertainty principle of Heisenberg, and the wave equation of Schrödinger. And so how does measurement enter this postulate? Now, measurement has always been a fraught subject in quantum physics. Schrödinger hated the quantum jumps. He hated the measurement stuff. He had this idea of the Schrödinger equation, everything is evolving according to this nice equation. Why do we need anything else? Well, so measurement enters quantum mechanics via a postulate, which stated that interrogating the system results in a final state that is a single stationary state or eigenstate of the measurement apparatus. This is really the work of Max Born and his contributions to this subject. So we give actually in the first chapter, historical review of all of this history that goes up into the current day. Going up into the work of, talking about the Einstein-Podolsky-Rosen experiment, the work of John Bell, and some of the subsequent work, trying to understand more deeply what quantum mechanics is telling us about the nature of the world we live in. All right, and so we can also go on into some of the great classic experiments. I call this the cigar of Otto Stern. This is the work of the famous Stern-Gerlach experiment, where they had a collection of hot silver atoms coming out, passing through a filter, and then passing through a fringing magnetic field. And what they thought would happen was that they would maybe be able to discover the orbital quantization of the atom. And what they found instead was what we now know is evidence for this fact that the electron has a property, a hidden property, electron spin. So we see that the atom are split into an upper beam and a lower beam corresponding to the spin of the valence electron of that silver atom. Okay? So the important lesson from this experiment is that even if I filter this into certain special states, eigenstates so-called, of the quantum system, we never can predict which beam the silver atom lands on, up or down. It's impossible to predict because identical experiments give rise to different final conditions. Maybe that's the most radical departure of quantum physics from classical physics. I'm going to repeat it. Even for the most simple systems, identical initial conditions lead to different final outcomes. Once you see that, you say, how is science even possible with that kind of system? And that's where we make the most radical break from classical physics. We don't try to describe individual events. We simply try to describe the distribution, the probabilities of those events taking place. Now, as a historical note, once they got this result, Stern and Gerlach, they sent this postcard. They put the data on a postcard and sent it to Niels Bohr saying, look what we found. So this, I think, is a very beautiful postcard from the Niels Bohr archives. And I call it the cigar of Otto Stern because they were having a hard time getting in the laboratory. You guys that are experimentalists know about this. The experiment wasn't working the way they wanted it to. The silver wasn't developing, but Stern found that if he blew his cigar smoke on the silver, it helped develop the silver into the nice black spots. So cigars helping early quantum mechanics be established. Okay, so one of the things we've learned about quantum wave function collapse is you might say, what causes the wave function collapse? So what does this even mean? Can we ask this question scientifically? And one of the surprising or interesting effects we found is that the wave function can be caused to collapse by something not happening. Okay, what do I mean by that? Well, I'll tell it through this allegory of Gregory, the Scotland Yard detective, and Sherlock Holmes, as accounted in the work of Arthur Conan Doyle. Gregory, the detective, says, is there any point to which you wish to draw my attention in this story? Holmes says, to the curious incident of the dog in the nighttime, to which Gregory says, the dog did nothing in the nighttime. And Holmes says, that was the curious incident. So something not happening can bring us information that may be critical, in this case, to solve a mystery. But the same kind of thing can happen in physics. So this is an example with the kind of systems I often work on, a so-called superconducting circuit made with a Josephson junction. This is a superconductor with a thin piece of insulator between the two superconductors, creating a macroscopic quantum system. And what's interesting about this particular kind of geometry made with capacitors and inductors is that the effective potential well that this quantum system lives in forms an effective two-level system called the phase qubit. So the energy landscape looks something like this metastable potential here. Well, the circuit, even though it's a macroscopic circuit, can be quantized. It has quantum energy levels. So the system can live in, for example, the ground state or the first excited state, or by applying some microwave control here, we can prepare quantum superposition of 0 and 1. And we can read out this quantum system by active tunneling. So the system in the upper level can tunnel out. If I lower the vary a little bit, for example, it can tunnel out of this upper level, but not the lower level. And so what can happen then is by preparing a quantum superposition, I can use this readout device to see if the quantum system tunnels or not. If it tunnels, then I can read it out with this inductive readout device. And what's interesting is that by simply listening to this detector that could click, but does not click, we can then say that actually this causes also the quantum wave function to collapse down to state 0. And what we can do then is say, how could I check that as true scientifically? Well, I could let that that tunneling happen and then come along, that didn't happen, and then come along and then check what is the correct state of the system with subsequent measurements and check how is the state disturbed. And so this is a way that people can then check that this wave function has indeed collapsed, or the ground state in this case, by something not happening. There are other ways that we've learned how to control and measure the quantum system. One is simply by taking another degree of freedom, we call it a meter, and letting it weakly interact with the quantum system of interest. Okay? And so by letting it weakly interact and then measuring the meter, we gain a little bit of information about the original quantum state. Okay? This is called the weak measurement. This is an area that's pioneered by Yakir Aronoff, who you may have heard of. And the idea is that if this is the state of the auxiliary meter degree of freedom, after the interaction there's a slight splitting. So one state of the system might shift the meter a little bit to the right, the other shifts it a little bit to the left, and so there's a slight splitting between the two things. Now you might think that any measurement on average would have to be bounded between the left peak and the right peak, okay, if I make an average measurement. But one of the things that colleagues Yakir Aronoff, together with other coworkers, realized back in the 1980s is that if the system is subsequently post-selected, so I measure the system by confining my attention to only one of the outcomes, then actually the meter doesn't have to be between here and here. It can be shifted many times the peak of those two, with the trade-off that I have to reduce the intensity of that meter. There are many fewer events that correspond to that post-selection. Okay, and so this is called the weak value effect, and this has been used together with my research group and other experimentalists to make very precise, for example, detections of the motion of a mirror. For example, if I have a very slight shift of a mirror of motion, then I could actually detect the optical shift by femtoradian angles using this kind of effect. So this is another application of this kind of weak value type effect. Okay, so this is another way that we're going deeper into the quantum measurement area. All right, so one of the things also people are very interested to do in the laboratory, we want to ask ourselves the question, what's the best measurement I can make? And the best measurement I can make is something called the quantum limited measurement. So what we can do is think about applying quantum mechanical principles to the amplifier I'm using to be able to then measure the quantum system I'm interested in. Okay? And so one of the ways people can do this is monitor, if I, for example, I have some bosonic degrees of freedom in my input, I have an amplifier, I have the output, what bounds does quantum mechanics put on the amplified degrees of freedom in my system? Okay? And so this is really a non-trivial task. So quantum mechanics, we can derive how this works, but then actually being able to build these amplifiers that saturate this bound is really quite tricky. So the design and operation of these detectors is a non-trivial task, but it's really a key part of the science, measurement science, especially at microwave frequencies, that many of these superconducting systems operate at. So trying to build quantum limited amplifiers with microwaves is really important.
Excuse me?
Yes?
What do you mean here by amplify? Like what is being amplified?
What is being amplified? Good question. So typically, I mentioned like you have these meters that get shifted a little bit to the right or to the left. And so one of the amplifiers in the superconducting circuits, the way they measure those circuits, is they have typically a cavity that the superconducting circuits are in. And the way we measure them is we put in radiation, electromagnetic radiation. So people generate microwave frequency radiation. They put it in, but they don't want to smash their quantum system with the radiation. They want to gently touch it. They want to just sort of tease out the information in a very delicate way. So they detune the frequencies of the radiation from the natural excitation of the qubit off resonance. Okay? And then you get something what's called the dispersive interaction. And when that happens, there's a slight phase shift. Your optical state picks up. It's dependent upon that qubit frequency. And you want to be able to then amplify that slight phase shift. Okay? And so that's what they're doing in these amplifiers. They're building electrical circuits to then take that electromagnetic radiation and say, can I amplify the quadratures of those radiation fields in order to be able to then measure in detail the system of my system. So that's one example in a circuit example. Other examples might be, so for example, I'll come back to the other example in a minute because I have a slide about that. But, so if I want to build an amplifier in the circuit lab, I might have this kind of system like this, where this might be some kind of transistor or nonlinear element with some gain lambda, and there's some kind of input, there's some kind of voltage, there's an output voltage. So this might be a classical circuit amplifier. And so what we can able to do is build quantum mechanical versions of this, where these are operators that couple input systems to output systems, and be able to use linear response theory to be able to derive fundamental limits on how to create these amplifiers. So one example of that is if we use linear response theory, there are two fundamental rates that come into play. One is how quickly you can pull information out of the system. So there's a rate of information gain. We call that gamma sub m. There's also a rate of how quickly you disturb the quantum system. We call this the measurement-induced dephasing rate. We call that gamma phi. And so you can bound, using linear response theory, the fact that I can't pull information out faster than I dephase the system. So there's an inequality on how this works, and the best detector will saturate this inequality. And so this theory tells you, if I look at correlations between these input and output variables, this tells you how to design a detector that makes the best use of this information. So we want the reverse gain, for example, to vanish. We want the real part of some cross correlator to vanish. And if I do that, then I saturate this inequality. So that's a theoretical contribution to this field. And then what we actually do is we actually go into the laboratory now and then build these things. So this is this field of quantum technology. So this is an example of a two-dimensional circuit chip that's made with a series of superconductors, resonators, Josephson junctions, and so on, to be able to control and manipulate these quantum systems. And you might recognize that from my book cover. This is an abstraction of my book cover from these kind of circuits that we can make. Right? So that's a two-dimensional version. Here's a three-dimensional version. Here's the Josephson junction circuit in the middle of a 3D aluminum cavity that we can then use to then control these quantum systems. So this is an example of what's called quantum circuit electrodynamics architecture with superconducting circuits. Okay. So let me talk now about a different kind of quantum measurement. This is something that happens all the time in the laboratory. It's what we call continuous quantum measurements. And this is when you interrogate the system not just all at once, like you would do in a textbook kind of way, but a continuous monitoring of the quantum system. So many new ingredients come into play. First of all, that noise is fundamental. We have to understand the nature of the noisy nature of this quantum measurement. And there are two basic types of continuous quantum measurements: diffusive quantum measurements and quantum jumps, which you may have heard of before, or quantum leaps. And the diffusive type comes into play where there's a quasi-continuous stream of data coming to the observer. Okay, so if I'm looking at a continuous noisy voltage from an amplifier, for example, that would be a diffusive type of quantum measurement. And there are two concepts here. One is the measurement record. So this is the amplified voltage showing up on my oscilloscope in my laboratory. I call this R of t, so some noisy signal that I get. But associated with that, there's something called the quantum trajectory. So rather than the quantum state being the same all the time, as I'm taking data in, I'm learning about the system all the time. So I have to change my mind about what the right quantum state is. And the dynamical update of that quantum state as a function of time is called the quantum trajectory. So that's the description of the quantum system conditioned upon my knowledge of what the measurement record is telling me. So that's a diffusive quantum measurement. There are also quantum jumps, and these are typically the kinds of jumps that happen if I have a detector that's quiet most of the time, like a photodetector, but occasionally I get a click, okay? And this is an example of a fluorescence of an experiment where I have a lamp is on, then it's quiet, on, quiet, and so on. And this is the quantum jumps of a three-level atom undergoing interrogation. And so whenever this atom is jumping between the states, it's emitting radiation. When it goes into a dark state, it's not emitting radiation. And so as I detect this, I then have the quantum state jumping back and forth between different quantum states. Right. So let me give you an example. So this is the other example I was going to give to your question a minute ago. So this is an example using solid state physics. And the idea is I have a two-dimensional electron gas. So this combines electrons to move in a plane, no longer in the bulk. But I can topgate this with metallic electrodes, so I can further confine the motion of dots, of electrons. And so here, an electron can be either in the left dot or the right dot, but there's a little energetic barrier here between the two of them, which allows tunneling to go back and forth between the left and the right dot. So the question I want to ask is the electron on the left dot or on the right dot? How can I measure that? Well, the idea is the electron has a handle on it, and the handle is the charge of the electron. And I can use that handle to figure out where it is. And I do that because as the electron is here, there's a capacitive coupling through this electrode to this small conductor. So there's a conductor here. It's like a small resistor. There's a source and a drain. I apply voltage across. I drive a current from bottom to top. And the question is, what current do I measure going through this circuit here? And from that current measurement, I can make an inference about where the electron is. How can I do that? Because if the electron is, say, the left or the right, there's a slight difference, I1 or I2, and typically I1 and I2 are very close to each other. That's the way I can tell where the electron is. So I measure position by current. But there's a catch, which this doesn't happen all at once because that process of current flowing from the source to the drain is not deterministic, it's a noisy process. And what happens is as the electron tries to go from here to here, it scatters. Sometimes it goes through, sometimes it reflects, and so there's a phenomenon called shot noise. It's related to the discreteness of the electrons. It's like if hail comes down on a roof, you hear the boom, 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 the individual noises of the hail balls. The same thing is true of the electrons going through this electrical circuit. And so because that's noisy, there's fundamental source of noise of my detector, so it takes time to know is the electron left or right, okay? And the way I can quantify that is if I take the power of that noise, the RMS power, the variance of that noise, we call that the shot noise power, and I divide that by the difference of these two currents squared, that has dimensions of time, okay? And that's a new time scale of the problem. So when I describe my quantum physics of this measurement, this time scale becomes very fundamental. I had to understand what this is, and you see that I can actually change what it is. I can make it very long. If I make these delta I very, very small, it becomes a very long time. I can make it very short. And so how long does the measurement take? That's up to you as the experimenter. I can make a very long measurement. I can make a very short measurement. And we'll see that that collapse time of the wave function is controlled by this time scale. Okay? So that's a new kind of theory. And so when I write down theories of the measurement, this time scale plays a fundamental role along with the Hamiltonian, the energetic time scales. Good. All right, so once we have this kind of technology built, we can then ask what happens. So here's a little movie I've made of a two-level quantum system. So I've drawn it on the Bloch sphere. So these are the Pauli operators on the vertices. And if I measure in the sigma x basis, this is like doing a measurement in this basis, my quantum mechanics textbook would say I get collapsed either to this state or to that state. And what happens with these continuous measurements, we can begin to write down equations that look like this. I'm not going to go into the details other than say that there's some deterministic part and there's some stochastic part. And this determines together how the density matrix or quantum state of the system changes as a function of time. Now what's nice is that once I have this approach, I can then begin to make movies to visualize how the quantum state is changing. So let me play a little movie here for you. So over time, I begin to collect information from my detector, and I can write down this so-called quantum trajectory as the state starts in a superposition up and down and gradually collapses to one outcome, say spin up, for example. So this is the quantum trajectory that corresponds to that. And what I've drawn here is I've drawn a single line together with a bunch of dots. Now the line is the result from my theory. It's from solving this kind of equation using a computer or analytically, given data from the experiment, from a given run. But then we can then check and say, how do I know that theory is actually describing the results of this experiment? What we can do in the experimental laboratory is we can stop this experiment partway through the experiment and then check what is the correct state assignment by doing subsequent experiments on that system. And the results of that data, that experiment data, is in these red dots, okay? So that's showing that we're able to then actually accurately predict and then understand what's going on in this experiment. And what I love about this is this allows us to peer into the inner workings of the quantum state collapse to really give a more detailed scientific understanding what's going on as we make a measurement in a continuous way, in a dynamical way. So it gives us greater insight into the physics of continuous quantum measurement. Okay. All right, and so we can continue to do this in other kinds of experiments. So these are more quantum trajectory experiments in superconducting circuits. I've drawn here 6 panels. On the upper panel, this is again a qubit type experiment where I have 2 levels. I'm drawing the coordinates of the Bloch sphere. If I do an ensemble average over all possible measurements, I get this kind of decay of my coherence to a mixed state. Or if I drive it, if I have a Rabi drive with some radiation at the same time, I get decay with oscillation. So this would be a more standard textbook type open quantum system. But with the monitoring, if we add together with real-time data acquisition, I can then improve my prediction rather than these curves. So this is an ensemble of over millions of experiments. This is actually data from a single experiment, one experiment, that I can write the quantum trajectory for the x, the y, and z coordinates as I drive it more and more. So here you see basically I get this collapse to one outcome. Here I get collapse, but I get oscillations with the collapse. So I get more oscillations, but it's a noisy oscillation because as I'm making the measurement, it kicks around the quantum state as I make the measurement. And so what you see here is actually, if you look carefully, there are actually 2 curves. There's a solid curve and a dash curve for each of the lower systems. And again, that's a way of being able to check. One is with the theory, being able to predict what this quantum trajectory is doing. The other is with the tomographically confirmed data. So I stop the experiment halfway through. I create a huge database of all possible experiments that I've run this experiment millions and millions of times, and then check what's the right state assignment given subsequent measurements, and showing I get nice validation of these curves from that large data set. So again, showing we have a scientific, empirical handle on this question. Yes?
This is like a random process, so how are you able to get one particular point of this? Because every run it's going to be different, right?
He makes a good point. He says every run it's going to be different, which is correct. So every run I would get different trajectory here. So what happens, the way it does is I run it one time, I get a particular outcome of the measurement voltage, then I create my theory to say what's the right trajectory for that given instance of that random voltage trace. And that's one of the curves here. The other curve, I do this millions and millions and millions and millions of times. I stop, say halfway through, and I look at all those subensembles that give me the same prediction for that point. I do subsequent measurements of that subensemble and check, does that prediction successfully predict future experiments, right? That's called quantum tomography. So that's what I'm talking about. Is that clear? Okay, good. So the analogy I like to give is that in the old days, we had a picture of, we prepare a quantum state, we do a measurement, one of a discrete number of outcomes occurs. So it's like I have a collection of butterflies, and I open the cage of the butterfly, and before I would just say, does the butterfly land on a left tree or on the right tree? But now with this additional sophisticated quantum measurement technology, we can track the path of the butterfly as it undergoes its circuitous flight from the cage to one of the trees. So it gives additional information. Now you might say, okay, Andrew, what is that additional information good for? How does it give us some kind of advantage? Well, so one, it gives us greater insight and understanding. The other thing I'll talk about in a minute is that we can actually use that information to then, in mid-flight, make some kind of course correction. And I'll talk about that also in a minute as well. Okay. So maybe I'll just mention one of the things my group has been doing over the years is working on a certain formalism to be able to make predictions of this. And we call this the stochastic path integral approach. And the idea of the stochastic path integral approach is that we have a quantum state description. which we parameterize with some coordinates q. We introduce some auxiliary variables, we call them p, so they impose this quantum state back action, and then to create some kind of action functional that looks a little bit like, if you're familiar with path integrals, a phase space path integral approach, but it's very different because these are quantum state coordinates. These are auxiliary variables. This thing that looks like a Hamiltonian is in fact not a Hamiltonian, but it encodes the probabilities of each of these paths and also encodes the quantum back action induced by the measurement. So this allows us to predict all these quantum trajectory statistics. What's also very interesting is that we can ask, if I extremize this action, if I look at the analogous thing of like the most likely path here, this actually predicts the most likely way the quantum system collapses as a function of time. And we can actually then make these predictions with this yellow dashed line. If I start here and I impose a final boundary condition, I end up collapsing down here. What's the most likely way the system collapses? So if I draw a small tube around any path, what's the tube that captures the most of these quantum trajectories? This is what we call the most likely path. And so we can actually then check experimentally, and we find very nice agreement with the data to be able to capture this most likely way the system collapses. This is just for pure collapse without any driving. I can actually also add driving into this. Okay, maybe I'll skip this. This is just how we do the data analysis to be able to make these pictures. But we can also drive it as we're also measuring, and we can get these kind of nice, interesting curves. So here are 3 different times of the experiment with the same initial and final boundary conditions. And you see that even though the system is doing weird things to meet this final boundary condition at the final time, you see the theory captures it very nicely with the experimental data. Okay, so we call this the most likely path, or the road most take. Okay, so let me go forward a little bit. One other thing is we can get additional insight into the nature of quantum physics itself. So one of the foundational results in quantum physics is the Heisenberg uncertainty principle, delta x, delta p bigger than h bar over 2. We all learned this in elementary quantum mechanics. But if we unpack this, what does this really mean in terms of operational experiments? What it means is we have a collection of experiments of a particle. One half of those experiments I measure position. The other half of the experiments I measure position, calculate the spread in both of those variables in the experiments, and then that spread will then satisfy this inequality. Okay? But there are other questions I can ask that are not addressed by this principle. So one question I was thinking about even 20 years ago is, what if I could measure both of those things at the same time? If I build a detector for position, I build a detector for momentum, I turn them both on and see what happens. Okay? So an analogous kind of experiment was done a few years ago in 2016, where they did the same kind of experiment but for a single qubit, for a single spin. So there's a detector where I can measure, for example, the sigma x and the sigma y of a spin at the same time. Now, how did they do this? They built one of these superconducting quantum circuits, but they coupled it to 2 different cavity modes of the same cavity. So there's a fundamental mode and there is an excited mode. And by amplifying the quadratures of both modes, they were able to then jointly measure these 2 non-commuting observables at the same time. Okay? And what does that experiment show? Well, so we had some theoretical ideas about this, but the experiment shows something very interesting. It says that if I measure both of those observables along the same axis, I measure the same, or say the sigma x observable, then I get the usual textbook collapse. I collapse either to this eigenstate here or that eigenstate there. But I can start splitting the angle between those 2 measurements, and what happens is that collapse point becomes a blur. It becomes some kind of blob, which I collapse to a variety of different states in some neighborhood of those two different measurements. But then if I continue to turn that angle farther and farther to 90 degrees, I make a mutually unbiased base measurement, maximally incompatible, like measuring position and momentum jointly. What happens is something very interesting. I don't get collapse to any eigenstate anymore because the measurements are disturbing each other. In fact, what happens, I just get diffusion on this circle. Okay? So the system state just simply diffuses around in an unbiased way around the circle, never collapsing anywhere. So one of the lessons is I can measure like crazy here with really strong strength, but if I'm doing this joint measurement, I never get collapse. I just get this diffusive kind of measurement. So I get this tug of war between the position and momentum. Okay, so some of the interesting phenomena of this, and I'll wrap up here in just a minute. I mentioned before it's possible to reverse a measurement. So here's a really fascinating thing. So suppose I start with some unknown quantum state in the experiment I was mentioning before. I turn my detector on for a while. You say, okay, I know I'm giving quantum measurement back action, so I've destroyed my state. Right? I have no idea what it is anymore. I didn't know what it was before, now it's something else I don't know. It's gone forever, right? No. The claim is I can actually undo that. How can I undo that? Well, if I have a detector that's efficient, what I can do is I imagine turning the detector on for some time, t. If I'm in state 1 or state 2, if I rescale the measurement output correctly, and I integrate it over time, this would be a deterministic path for state 1. This would be a deterministic path for state 2. I can reason in a kind of Bayesian way and saying, well, the reason I got here is I could be in state 1, and I get a drift up this way. But I could be in state 2. I just get some kind of fluctuation that takes me up here because my detector is random. So the central idea is turn the detector back on and wait until this process, this detector outcome that I have in my laboratory, goes back down and crosses the origin again. If it does that, the claim is I've restored the state to what it was in the beginning, even if I had no knowledge of that state. Okay? So in that sense, the accidental measurement can be undone by waiting until this crosses the origin. Okay? So the idea schematically is this. I start with a state I don't know. I get some kind of partial collapse to some other state I don't know. But under the appropriate outcome, the appropriate experimental outcome, I can restore it to what it was, the green light. But I also have some indication that I could fail and I get something else. Here the indication I would fail is that I keep waiting. It never crosses, it just keeps going up and up and up and up. That would be failing to undo it. Okay? So this has actually been experimentally verified in 2 or 3 different experiments, the fact that I can actually undo the measurement. Now this is really, I think Bohr would be shocked by this. There is a catch though, and the catch is that if this first measurement is very strong, if it takes a very long time, then it's very, very unlikely that I come back and cross here again. So I actually reproduce irreversibility, but only in a limit of an infinitely strong first measurement. Okay. I mentioned quantum technology. I think I'm going to skip this slide just to mention that people are working hard to develop all kinds of circuits to do quantum computing, quantum control, quantum measurements, and there's a race on to build the quantum computers with these kind of systems. But I just want to conclude with some nice experiment. I mentioned before that I can actually stop the experiment halfway or some part of the way and do feedback and control. So this is a really nice experiment that we did together with Siddiqui's group a couple of years ago, where I can do quantum error correction, but in a continuous way. And the way it works is, this is a 3-bit error correction protocol. I encode my logical state in 3 physical qubit states. And then what I do is I don't measure each of the qubits because that would destroy my state. What I do is I measure the parity of these qubits. I check about the parity of qubit 1 or 2. And what I mean by parity is, is it 0, 0, 1, 1, or is it 0, 1, 1, 0? Okay, so the first one would be the even parity. The second would be the odd parity. And so if I so I can make a measurement where I couple these 2 together in one cavity, these 2 together with a different cavity, and then turn them both on the measurements at the same time. And this way I don't disturb the logical state of the qubit. I only check to see if an error is introduced by the environment. And what's nice is because I have a continuous outcome, these guys tell me about the resonator voltage signals. I can tell down here this is no error. If there is a 1 bit that gets flipped in the qubit 1, 2, or 3, it'll take me to these error subspaces over here. That's bad. But by watching in real time, all the time, I can see, does it wander over here? And if it does, I can say, aha, I'm going to send in the correction pulse to fix that. I send in the pulse to flip it back to where it was. And I draw it back into the no error subspace. So I can then prolong my coherence using this continuous quantum error correction. So it's an example of using feedback and control together with the continuous monitoring to do a quantum information task. All right, so just to conclude, we end with thinking about these philosophical questions. What does it all mean? What have we learned from this about the nature of reality? And there are many interpretations of quantum mechanics that have been raised over the years. Each of them have various strong and weak points. Likely, I think they're likely all wrong. We typically, we found the most productive way of thinking about it is to view the quantum state as a reflection of our state of knowledge rather than something that exists out there independently of us. In other words, we're using the formalism. When something collapses, it's actually our knowledge of the system that causes us to collapse, and then that allows us to then correct our state assignments consistent with that. So with that, I'll thank you for your attention. I'm just going to mention, I think I'll skip these reviews and endorsements of the book. This is a great little cover story for my brother. My brother made the cover. This is some of his work. He took this circuit from Irfan's book. This is about the cover. It's my little art science vignette. And he is inspired by these two artists. So this is Frank Stella. He just died last year. He's an American artist. He drew lots of these beautiful geometric pictures. In fact, in my institute, we have one of his works in my institute in Chapman. And he was also inspired by this guy, Joseph Albert, who's a German-American. This guy is really interesting because he built his whole career drawing squares. This is like he drew squares and squares and squares. He wrote like hundreds and hundreds of paintings with squares. So it's really a testament to persistence in art, I guess. But he took these two inspirations and then was able to then take these kind of circuits and then being able to draw as an artist, taking some inspiration from these circuits to be able to design these kinds of beautiful abstract quantum circuits. This is abstraction. And you see some more, just for fun. You see the artistic process. Okay, so with that, that's the cover story. And just to give a teaser, I'm here also visiting Ricardo. Where's Ricardo? There he is. There's me, together with other great people. We're writing a nice perspective about unraveling quantum physics measurement in the 21st century. This is a perspective for nature. I hope will be coming out very soon. So something for you to look forward to with your new young professor here. So thanks very much for your attention.
And it seems to me, which I am ignorant in this, that there is a set of a number of measurements taken at different times, and to reproduce the trajectories, you are actualizing each time from the previous measurement. Is that correct?
That's absolutely correct, yes. Yeah, the idea is that in any random process in nature, things are never truly like a continuous random process. We have a discretization time. So in the experiments, there is a time scale which the detector can respond in its most fast way, right? So that's about a nanosecond. So that's basically the time scale they digitize the information on. And they stitch those together to get a quasi-continuous process. But you're right, we're basically updating from state to state to state. And there's an assumption there that goes into the theory of this, that this is what's called the Markov process, that we don't have memory beyond the previous state. And of course, you can get into a regime that fails, but for these experiments, it's a really good approximation.
Thank you for your nice talk. But what could be the real meaning of the trajectory? Because in classical physics, when you have a trajectory, then you have velocities, accelerations, forces, energies. From that kind of quantum trajectories, you can also obtain those velocities, accelerations, and is that in the same way that Copenhagen interpretation? Because Copenhagen interpretation is just probabilistic.
Yeah, Great question. So this gets a little bit into the interpretation of what it means. And I think both in the talk, but also in the book, we're very clear in the bulk of the scientific discussion, talking about only things that we can then check in the laboratory. So we can check that these trajectories occur and the changes occur. But to go further, so you mentioned things like velocity and position. So remember, I'm writing down the trajectories is for the quantum state itself. But what I can do is I can say, I can take that trajectory, or that state, and then say, what's the expectation value of the Hamiltonian, for example, with that state? And that gives me my estimated energy. And so what I'm saying there is my energy is going to fluctuate as well, right? And so there are physical consequences of this. And so the fact that I'm going to be essentially, the reason that happens is essentially I'm exchanging energy with my measuring device. Okay, so there are energetic consequences. There are consequences in terms of momentum and position, things like that as well, more generally. Now, there are different ways of thinking about it. So one way of thinking about it is it's like a Brownian motion. So if you think about it, a Brownian motion, I have a pollen grain, atoms are colliding with it, the pollen grain is jittering around. I'm exerting forces on that grain from the atom. Right? So that's one view. So if you have like a realistic view of the quantum state, you say that's something that is happening here. My measurement is coming somehow, my measurement meter is somehow coming along and giving it little kicks like a Brownian particle. That would be one interpretation. I don't think that's the right interpretation, but I think you can have that interpretation. I think the better interpretation is to say that as this state is moving around, I'm simply learning a little bit more about the quantum state, and I'm adjusting my knowledge about the quantum state based on that. Okay, and that, of course, that knowledge does have physical consequences, but I think people can disagree about what that means. Okay.
So you mentioned the time scale for measurement, and you gave an equation that was very specific to the experiment. But I'm curious if you have a formulation, like a more general formulation, and also like what would be the consequences of that time not being zero?
Yeah, great question. And so so this is one of the messages of the book. People say, okay, if measurement is continuous, the wave function takes place over time, the natural question is how long, right? And so in that experiment, I gave a formula, but the answer is it depends on the kind of measurement you're doing, right? So one other example would be, for example, if I have a spontaneous emission, and I'm monitoring the emission of an atom to figure out what the atom is doing, then it's that decay rate, that's the half-life of the atom, that's then the measurement timescale. So each experiment that I do has a different timescale based on the kind of measurement I design, okay? And that's something that's also very non-intuitive and surprising, that depending on the kind of measurement I do, I can make that quantum trajectory do very different things. I can make it jump, I can make it diffuse. It's up to my control as the experimentalist, right? Which for me is another indication that maybe the quantum state is not the final description of if there is an underlying description of nature as a realist description, but it's a measure of our knowledge about the quantum system. There may be something deeper, a deeper formalism that tells more, maybe.
There is this Mandelstam term like inequality between energy and preparation time that I have really never understood very well. But this could be related with the time that you are introducing before in the preparation time.
Yes, so my understanding of Mandelstam TAM is that basically it says I have a certain amount of energy I can give to the quantum system, and then that then controls the limit on how quickly I can move the state from a given state, say, to an orthogonal state. All right, so there is some energy budget that I have to give this, so that actually timescale is really important in the theories of quantum metrology and things like that. It's related to it's a way of formalizing the time-energy uncertainty using this concept. Here it's a little bit different because I'm bringing in other degrees of freedom here, so I have other resources that I can give for my quantum measurement, for my meter, and so I think it goes beyond the Mandelstam TAM time. Okay.
Gaston?
Yeah, well, nice talk.
Thank you.
I have two questions. One is, what is your view of the many worlds interpretation? And second one is, what is your view on retrocausality?
Okay, great. We're getting into quantum foundations. So that's like let's see. Yeah, this is my slide here. So I have, okay, it's like I have really good friends that are really big many worldser. So I don't know if you guys know a guy named Lev Weidman, but he's maybe the most outspoken many worlds physicist that I know of. I went to his meeting in Israel a few years ago on many worlds. I personally don't believe in it because I just don't think it's a really good description of what's going on. So if you don't know what many worlds is, it's an interpretation of quantum physics. It says basically every time there's only unitary dynamics, there's no measurement, there's no collapse. But every time something like a measurement happens, the whole world splits into two. So I have two worlds. So in the Stern-Gerlach experiment, when the atom hits the upper spot or the lower spot, those correspond to the worlds branching, two different worlds. And so they never touch back to each other again. Okay? And so essentially you have to say for every possible event that happens, there are an infinite number, essentially that many worlds exist independently of each other. And essentially that for me, that's like, the cure is worse than the disease because it creates this infinite set of things I can't observe that to describe a problem that seems to me not a problem. The second question is, this goes back to this question about maybe there's a deeper theory. So maybe quantum mechanics is not the whole story. Indeed, in the last chapter of my book, I have a section of my book called Beyond Quantum. Because I think quantum mechanics is not the final world, not the final world, not the final word on physics. I think there can be more beyond it. And what might that look like? And one of the things we might have to rethink is our concept of time. And so possibly if not retrocausality, maybe some kind of retro influences. And I know, again, I have friends that write papers about what if the future can affect the past, right? And so I mentioned Yukiro Aronoff. He believes in some kind of version of this where we can't know what the future is, but there's a correlation with the future that affects us now. I know other people that say, I can have a realist description. I can write down properties of systems that exist independently of us if I allow influences from the future. I'm not ready to go there. I don't believe in it, but my mind is open. And so people could give me good evidence, or maybe I'll think of good evidence why this could be a thing. I'm open to that. But as far as I know, I don't see any evidence that makes us adopt that position.
Yeah, well, you mentioned earlier in your talk this new time scale that we need to take into account in this measurement theory. I wonder what is the relationship of this new time scale with the Markov approximation? How does this take place?
Okay, good.
Thank you.
Yeah, so the time scale works together with Markov. Basically, it says I can write the correct quantum description as a dynamical process using only the previous time. And typically the collapse, if I just do plain measurement, the collapse happens on that time scale, okay? But if I do non-Markovian physics, I have to go beyond that. And the reason is, I wrote down one of the equations earlier, and it was a time-local equation. It says, what happens next time only depends on what happens now. But if I have an example, for example, if my cavity that I'm doing the measurement is a very long-lived cavity, it's a really good cavity, the photons stay in there a long time, what happens now doesn't depend just on the previous step, but there's a long tail of influences that it depends on way back in time. And the reason for that is very simple. It's that in that example with the photon in the cavity, that photon lasts a long time in there, bounce, 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 bounce. And so what happens now could have an influence from a photon. The photon interacted with that atom, say, a minute ago, but it's just now coming out of the cavity, right? And so I have to have a whole history to be able to describe that. So it's basically, it goes beyond just one time scale. There's a whole history that I have to take into account as well to get good predictions.
Thanks.
I was wondering how this model for
the evolution into wave function collapse could explain sort of, what's the word, decoherence. How would decoherence fit into this whole picture?
Okay, this is a great question. So often when people think about continuous measurement or open systems, they think about decoherence. And this was really popularized by Wojciech Zurek and colleagues in the 1980s. And again, there's a history of that in the first chapter of my book. This goes beyond decoherence, because decoherence basically says I have an environment, the environment interacts with my system, it gets random phase kicks from the environment, I can't measure the environment, so I see decoherence, I see my system lose decoherence, it becomes a mixed state of my system, okay? So essentially it's a loss of information because of my environment is unmonitored. But what's happening is different here is that I take all that environment and I structure it, I put it into a very special kind of environment that I can monitor. I can monitor all those degrees of freedom in a way that I have access to. That gives me a predictive advantage. So those pictures that I was showing, you see, maybe you remember the trajectories I was showing, the averaging of everything became decoherent very fast. If it was a single trajectory, that remained pure almost the entire time. So what's happening is that decoherence theory is all about loss of information. This is all about how I can gain information. I gain information from the environment, and I get a predictive advantage. And when that happens, I don't have a mixed state anymore. I have a pure state. I can actually purify the state by learning more and more about the system and conditioning on that result. So it's a good question. And so they're related to decoherence theory, but it goes beyond decoherence theory.
Thank you.
I was wondering about the Zeno effect, in particular in the case of negative measurements, because if you have an excited state and you never measure, it will never decay. So how does this connect with your vision?
Yeah, so this is a great question. And so, so there is also a discussion of the Zeno effect in my book as well. And what that means is basically that, say I have a state that I start in, and many other states I could be in, if I'm measuring the system strongly in that state, even if I have a Hamiltonian that takes me to the other states, I keep projecting it back into that initial state over and over and over again. And so I freeze it in that state, essentially, okay? And so occasionally I can jump, but it's on a much longer time scale, okay? And so, so essentially there can be versions of this where I can have a continuous description of quantum Zeno. And the important thing there is it's the time scales involved. So there's a time scale of the unitary evolution. There's a time scale of the measurement. And it's how those time scales compare to each other. On one time scale, the measurement's much stronger than the unitary. I get a continuous Zeno. I get pinned into this one state, and occasionally I jump to other states, right? But on a much longer time scale. And the other limit, I get basically a unitary evolution, but with some diffusion around it. So basically the unitary is winning, the measurement just gives a little perturbation. So I can tune back and forth between these two different regimes by controlling these time scales.
So I think that's a great moment to finish. And let's thank Andrew again for his beautiful talk. And for everyone interested, tomorrow we're going to have a more technical seminar of a particular paper and a given set of ideas at 3 p.m. in the Sala de Emeritus. All right. Thank you very much, Andrew, again. Thanks, everyone, for joining us.
Thanks.